All right. So next speaker is going to be the first Jonathan of the afternoon. It's going to be Jonathan Conrad from Berlin. We're talking about codes from NTRU-GKP.
Yeah. Can you hear me okay? Let's see if this works. Okay, yeah, thank you very much for the thank you very much for the nice introduction. And also thanks again to all the organizers for organizing this very nice conference, at which I feel very much at home. So this is a conference, this is a talk about so merging the GKP code with lattice cryptography. You cannot hear me? Okay.
Microphone's very directional, so
This is
turn your head
very
careful.
okay. So I'm gonna have to look down like this. Okay. So yeah, so this is gonna be a talk about merging GKP codes with a certain.
Maybe just like on your shirt.
I can just hold it. Yeah. Sorry? Oh, should I just like? Okay. Yeah. Okay, so this one is not directional. Okay. Okay, yeah, sorry for the delay. Okay, yeah, so this, oh yeah, that's so much better. So this recent work that I've been working on together with Jens Eisert and Jean-Pierre Seibach, who've been very nice collaborators. And Jean-Pierre in particular is a great expert on crypto and on lattice theory, from whom I could learn a lot. Yeah, so this is going to be a fairly like coding theoretic and basic GKP kind of talk. So I want to start this talk by going back into history a little bit. This is very recent history. This was the last BBQ meeting. Since when? So this was a welcome meeting at the beach at the last BBQ. It was really nice. And since the last BBQ meeting, a lot has happened in GKP quantum computing. There have been very impressive experimental demos. There has been a bunch of theory work, in particular on concatenating GKP codes into larger qubit type quantum error correcting codes, and to see how you can improve that, how you can get the best out of GKP, maybe towards something more scalable in the future. But the basis for all of these like very recent developments were really set in these three papers that I outlined at the very right. So the first one, all of you know, that's the original GKP paper, where they don't just propose the square GKP code, but they propose this general framework of GKP codes on constructing discrete logical subsystems of multi-bosonic systems using displacement operators as stabilizers. So this is like the very general framework that they already investigate, and everything in principle is all there. Yeah, it's just been taking many papers to decipher what was going on. So very, very shortly after the original paper, Jerome Harrington was wrapping up his PhD thesis, and he's made some very interesting explorations into the very abstract lattice theoretic coding theory of GKP. And some of the things I want to highlight a little bit more, and this whole cryptosystem thing is going to be about fleshing out a slightly more practical aspect of the like extremely theoretical work that Jim has been doing. Okay, so when I started working on GKP, I knew square GKP. Maybe at some point I learned about the hexagonal GKP code, but I was always too scared to look into the paper and really try to dig into all of this multi-mode stuff that they already do. And it took a while until Francesco up here joined our group, who provides a strong incentive to look at the things and to see what we can squeeze out of the general formulation of that theory. So Francesco is going to join Paris very soon, and as a GKP coding theorist, maybe you guys will be interested in talking to him. Right, okay, so how does the GKP code look like? We have n bosonic modes. We're going to choose two n stabilizers, which are all displacement operators that act on those n bosonic modes. Yeah? So these two n displacement operators all displace in linearly independent directions. And you want to choose them so that all of these displacement operators commute. So the first observation that you can make by simply computing this group, so you take integer powers of all of those generators, is that the group, by just combining displacement operators to form larger displacement operators, you see that this group is really one-to-one with a lattice. Yeah? The lattice being anything that's isomorphic to z to the m. Yeah? So this lattice here now describes the stabilizer group of the GKP code. Naturally, we don't want to do computation. We don't want to just like stabilize something, but we want to do something. So we also need to care about the centralizer, the stabilizer. So the centralizer of this GKP stabilizer group is given by the symplectic dual lattice of the lattice that specifies the GKP code. So this consists, again, a lattice, again, a 2n-dimensional thing, and consists of all the vectors that have a symplectic integer inner product with every vector in this stabilizer lattice. Yeah, and so these are really the core two structures that you're going to have to work with. So to do actual computations and to understand what's going on, you can write down a lattice basis. So you write down all of these 2n vectors into a matrix. You can compute a symplectic gram matrix that is just to say to what phase the individual displacements in the stabilizer commute. And naturally, if you want all of them to commute, they need to commute to something. The phases need to be some integer multiple from 2 pi. Here I crossed out the 2 pi thing, so everything just needs to be integer. In other words, the symplectic dual lattice describes all of the displacement operators that commute with all of the stabilizers. So that's a centralizer. And if you want the GKP code to consist of commuting stabilizers, then you want the stabilizer lattice to be a sublattice of that lattice. Yeah? So in these words, you can sort of classify the GKP code as weakly symplectically self-dual codes. Yeah? The symplectic gram matrix that I told you about earlier tells you how the generating set for the GKP stabilizer lattice embeds into its own dual lattice. So it's a sublattice and some integer matrix. Here, that just tells you, okay, how to combine the vectors from the dual lattice to get stable lattice. Okay, so now we have the sublattice structure. But in the sublattice, there are many logically equivalent displacement vectors. So one thing that you can look at is you can take this symplectic dual lattice, you can mod out the lattice corresponding to the stabilizer group, and you get a state of a representative set for logical Pauli operators of the GKP. The whole trick on computing how many dimensions we're actually ended up encoding is by computing how large the set is, which just corresponds to the determinant of this matrix A, square of that is the number of logical dimensions that we encode. So this is just a rewrap of how GKP works. Okay, so this is that was the general construction. So we come to a few examples. The first type of GKP code, which is the example that everybody knows, is the class of GKP codes that we call scale GKP codes. Yeah? And this construction works in this fashion that you take some symplectic matrix. Yeah? So and you interpret each row vector in the symplectic matrix as a basis vector for the lattice. So this defines you a symplectic lattice, and that it is symplectically self-dual. So every basis vector has a unit symplectic inner product with every other basis vector. So when you do the computation that we just outlined, what you're going to compute is that this encodes nothing. I mean, it encodes a one-dimensional state. So one example is the Q0 state or the sensor state. This is a GKP state that is stabilized by such a structure where M0 is simply the generator for the normal 2D integer lattice left to the 2. So that's the most trivial example that it can come up with. So now if you want to encode a qubit, well, they came up with a very smart and simple trick, is you simply rescale this integer lattice. So you rescale this lattice by a square root of some integer lambda. What's going to happen is that all of the stabilizers are getting longer, right? And all of the vectors that have a integer inner product, symplectic inner product with all of those vectors get shorter. Yeah? So you scale the vectors in the stabilizer group up by square root of 2, for instance, and all of the logicals get scaled down by 1 over square root of 2. Yeah? So this way, so the thick lines here in this example correspond to the ordinary GKP stabilizer group. This is not a state, this is just a representation for the group. And the dotted lines correspond to the centralizer of that group. Okay, so this is the structure that we have. The shortest logicals you can look at correspond to, like, for instance, the first shortest vectors that we have down here. And we now know how much we are encoding. We now know what the dimension of encoded qubit is, or qubit, or whatever system is. And we know how many modes we have used. So the next metric in quantum error correction that we need is some kind of distance. Yeah. one distance that you can define is you simply look at the Euclidean distance, assuming some displacement type error model. You take the Euclidean distance of the shortest logical operator that is not a stabilizer. That's a good notion for a distance. And in this kind of construction, it simply turns out that this Euclidean distance is given by the scaling parameters that you have and the length of the shortest vector in the symplectically self-dual lattice that you started out with. So this is really the non-trivial part about the computation of these distances. And one tour de force that Harrington and Preskill did in 2001 is that they realized that you can actually prove that symplectic lattices exist such that the shortest vector length scales with square root of n being the number of modes. So the reason why this is relevant is that if, for instance, you look at Gaussian displacement errors, the typical length for a Gaussian displacement error in 2n dimensions is going to scale with square root of n. So if you have a distance that, so if you want all of these errors to be correctable by simple arguments, you need that this distance also scales with square root of n. So it's a very complicated proof, and they effectively proved that these kind of lattices exist. And so therefore, yeah, I mean, they had some coherent, some information theoretic statements that you can get from that. So this is the type of lattices that we would call good GKP codes. Yeah? Good GKP codes are in this construction. Say, for instance, you fix lambda to 2. In this case, you'll always get a multi-mode GKP code where the number of logical qubits that you're encoding scale with the number of modes that you're using. So it's an encoding rate of 1. And we want the lambda 1, the shortest vector length of the starting lattice, to go with the square root of n, the number of modes. And there's this motivation why we call this good. On the one hand, it's pretty good because you can construct, you can correct against all typical Gaussian displacement errors. But we can also come up with a separate comparison. That is, if we look at concatenated GKP code. So in a concatenated GKP code, what you do is you take some qubit code, some ADPC code, or the toric code, whatever you want, and you replace every qubit by a GKP qubit. Yeah, so every stabilizer or every Pauli that you put into the stabilizers of qubit level error correcting code, you need to replace by the corresponding logical displacement operator of the encoded of the underlying qubit. So what you're going to end up with is you're going to end up with a huge stabilizer group with a bunch of displacements. So again, this is a stabilizer group generated by displacements. Again, you will have this large lattice, which needs to be weakly symplectically self-dual. And all of this is, again, just a bigger and more complicated GKP code with a clearer structure. Yeah? And so you can do this concatenation, and we can do the same computation as we've done in the previous page. We look for the shortest length of a displacement, which corresponds to a displacement, which commutes with all the stabilizers, but it's not a stabilizer itself. And you compute this, say, for instance, for the hexagonal or for the square GKP code, what you're going to end up with is that this Euclidean distance that we've just introduced really scales with the square root of the distance, the Hamming distance of the qubit quantum error correcting code that you've put on top. Yeah. So here you can realize why we call this good in the previous page. Yeah. If this Euclidean distance scales with square root of n, you have a code that has the equivalent distance scaling as a concatenation of the single mode GKP code into a linear distance qubit quantum error correcting code. Yeah. So this is really good, and this is what Harrington-Preskill showed exists. They didn't show that a concatenated version exists, but they showed that this kind of scaling exists, and that good GKP code exists. So this is a valuable thing, and that's something that we're gonna try to go after. Before we come to the explicit construction, I want to go to the next step of quantum error correction. And so in quantum error correction, what do we need? We need a code, and we need to be able to decode. Yeah. I'm not going to talk about how to measure stabilizers. That's much more complicated. So for the task of decoding for GKP codes or for any qubit quantum error correcting is such that you start with a code state that has been susceptible to some error. You input some assumption about a noise model. Yeah. And so you have one bit of quantum information, and you have one bit of classical information, and you're going to feed this into this machine, which is the decoder, and you want the decoder to spit out the original logical state that you threw in before the error happened. So, of course, this is just the abstract construction. What you're going to do in practice is you're going to measure stabilizers, and you're going to construct a classical machine that takes a syndrome as input, that takes the assumption about the noise model as input, for instance, a Gaussian displacement noise, and it's going to output an error that you should correct. So one way of doing that is that you can find a generic correction for the GKP code, for instance, that undoes your syndrome. You can always find this efficiently. It's just a matrix inversion. And then you just try to look at, okay, what logical translation was that vector the closest to, assuming or not the closest to, but was most likely close to. Let's put it like this. So which co-set of logical displacements was this closest? So this is expressed as these like lattice data functions up here. So this fairly complicated expression, and this is extremely hard to evaluate. Hidden in the coefficients of these lattice data functions are sharply problems. So this is something that you don't actually want to compute on a computer. What you can do, which is slightly easier, is you look at the limit of where you have small displacements. So you take sigma to 0, and you'll see that you get another hard problem. So now we've broken down this maximum likelihood decoder problem to what's called a minimum energy decoding. Barbara calls it that, which for the GKP code really just corresponds to the closest vector problem. So those of you who have thought about complexity theory or about post-quantum crypto also will know that this is, again, an intractably hard problem. So decoding is really hard for GKP codes, in principle, in general. Okay, so, and the reason why this problem of the closed vector problem is hard is really because it's a problem that gets easier with the right choice of the basis. But for a lattice, this is an infinitely large thing. We have an infinite choice of bases that it can choose to define the basis for your lattice. So yeah, so finding the right basis is simply an intractable kind of problem. You know that if you have a good basis consisting of short vectors, then rounding to a closed vector is easier relative to if you had like a lot of those very long vectors. So this is really a difficult problem, which motivates the problem of finding GKP codes that somehow naturally come with efficient decoders. One example we've already seen, right? One of the examples of GKP codes that come with efficient decoders are concatenated GKP codes. It simply takes the inherited qubit-quantum qubit decoder. We can, of course, boost their performance a little bit by using GKP information or something like this. But really, the workhorse in this kind of scenario is the smart design qubit decoder that has already been proposed. Okay, so this is really the background on all of GKP. So now I'm going to come to the concrete construction. I'm going to check quickly how am I doing on time. Oh, I didn't start my thing. Okay. 8 minutes. Okay, so I'm going to have to go through this a bit faster than I was hoping to. So what we're going to do. So Harrington-Preskill proves that there exists symplectic lattices with a square root of n scaling. There exists another statement when you look at lattice theory, which is called the Gaussian heuristic. So this statement up there, they're obtained by simply averaging over the moduli space of all symplectically self-dual lattices. And you can construct a measure for that, you can compute that, and you get the square root of n scaling. So by that, they prove the existence. The Gaussian heuristic, which most of the people mostly believe is true for good constructions, says that, okay, if you don't have like fully random lattices, but just sufficiently random lattices, this scaling we expect should still hold. Yeah, so we need to. So if you have some like pseudo-random way of generating lattices, then we still expect to have this kind of square root of n scaling. So this is the motivation of why we want to look at random lattices in order to get good GKP codes, square root of n scaling. Where do we find good lattices or random lattices? Well, lattice crypto is the place where we look for random lattices, because if you want to encode something into a lattice problem, you always use the same lattice. Then like one person just sits down and looks at that lattice very closely, and the security will be gone. Yeah? So lattice crypto is really the place to look for good constructions of random lattices. So the cryptosystem that we identified that's most useful for us is called the NTRU-GKP. It's a polynomial or factorization of polynomial over rings-based cryptosystem, and I won't have the time to flesh out all the details. So effectively, you take some nth degree polynomials where you define some quotient, like x to the n plus minus 1, for instance, which just says, okay, I define a polynomial, and every time I have x to the n, I'm just going to replace that with 1. Right? This way you can collapse every polynomial to like a finite number of coefficients that you need to look at. So what you're going to do, so you also have two other numbers. You have a large number q that goes with the n, and you have a small number key. So these are just other security parameters of the crypto system. And what you're going to do is in executing this crypto system is that you're going to sample random keys, F and G, from this polynomial ring, such that F is invertible and the coefficient vector of the polynomials is short. And then you're going to compute a public key, which is simply G divided by F, modulo stuff. Yeah. So, so what you're going to do is that you're going to, I think I didn't include exactly how the deciphering and the encoding and so on works, but for now, this is all we need to build the crypto system. Okay, so this crypto system has a feature that you can map it onto a module lattice. So this is now a lattice over these polynomials. And again, you can simply, by replacing every polynomial by its coefficient vector, you can map it to a lattice in R to the 2n. So this way you're going to end up, I'm not going to show now how this works, but you effectively actually end up with a lattice that turns out to be symplectic, which is what you needed to construct a GKP code with commuting stabilizers, which looks like this matrix up here, and H corresponds to the public key. Yeah? So this is the GKP code, which maps every instance of the crypto system to a realization of a GKP code. One other feature is that it has a sublattice so that you can interpret it as a qubit concatenated code. So these are all details. So the next thing we want to do is we want to check if the Gaussian heuristic holds. So if we get the square root of n scaling in the distance, I did some numerics for a bunch of different realizations of this crypto system, and you see everywhere that you get something of a square root scaling. Yeah, so both the red and the blue line all correspond to the square root scaling, and in particular, as in the very bottom layer or in block C, you'll see that we always maintain the square root scaling. Therefore, most of the instances of these codes actually have a good distance. So the statement here really is that cryptographic lattices are sufficiently random for square root of n scaling. One very important feature of these codes is that you sample a random error, you do a pre-correction corresponding to the sublattice, and what you'll actually find is that using the public basis for these codes, the syndrome that you're gonna measure actually corresponds to a ciphertext of the crypto system that we started out with. And this is a ciphertext that encodes the error that we have thrown onto the GKP state as the plain text. So the secret message is the error, and the syndrome is the ciphertext. So in this kind of situation, what we can identify that in order to decode this corresponding GKP code, we need to decrypt the crypto system. Yeah, so there's this really weird back and forth. And the crypto system is really just set up such that it is easy to decrypt the crypto system if you have the secret keys, but it is hard, it's provably hard for specific instances of these crypto systems. It's hard to decode it with only the public key. Yeah. So now we have constructed a GKP code that's hard to decode, but it's easy to decode if you know the right thing. Yeah. If you have sampled, then it's easy to decode. So we're going to use this to propose. We did some numerics on a very small dimensions. You know, the distance statements that we had were asymptotic statements. So on like very small, below dimension 100. Also, the performance as a quantum memory is not very good. But what we're going to do is we're going to propose to use these codes as some kind of a code-based cryptography protocol. Yeah. So here's a private quantum channel that we're proposing. So, and this works like this. Just let me explain this in 2 minutes. So Alice wants to be communicated to. Yeah. So she samples the secret key and of the NTRU crypto system and computes the public key. And releases the public key to whoever wants to communicate with her. Bob, who wants to send Alice quantum information, produces a GKP code state in that prescribed code, in the code that's prescribed by the public key that Alice has told Bob. Yeah? And then Bob is going to apply a random displacement corresponding to a secret message that needs to be encoded in the crypto system. Bob sends the state to Alice. So now Alice, what she's going to do is, well, I mean, Alice knows the secret keys. So Alice can measure the syndrome in the public basis and then use the secret keys to decode the ciphertext and by that undo the error and get back the logical information or get back to the full logical state that Bob has put in. but by the assumptions on the computational complexity of the underlying problems, anybody else who intercepted this quantum message and has only access to the public key would not be able to decode the quantum state. So this is a really weird and funny code-based cryptography kind of situation that we're cooking up. I have to highlight that we haven't like fully proven its quantum security, which is hard because it's relying on computational assumptions, and there's some like circular argumentations that you end up with when you try the naive things. But so that's under this like abstract level decoders that I've highlighted earlier. But at least for like the MED version of the decoding task, you can in principle prove security based on assumptions on sharpness of ring learning with errors or ideal. So we have some argumentations and discussions on in how far is this actually quantum secure, which I think is an interesting question. There are a bunch of interesting directions to go with these kind of constructions. There are homomorphic versions of this NTRU system. I have a proposal that I'm working on, what I call blind quantum error correction, which is a like Michaelis version of GKP for those who knows what this is. If you don't, come and talk to me. Yeah, so I'm not going to talk about the rest. All I hope is that I have been able to stimulate that there's a really exciting and interesting intersection between GKP quantum error correction, GKP coding theory, and crypto. That's very interesting to explore. And yeah, I think I just stop here, or I get beat up. And yeah, these are bouldering pictures. I'm bouldering stuff.
Oh, this is on? Yes, okay. So with these good codes that you have, do you have any sort of insight into whether they're relatively low GKP stabilizer weights?
Oh,
No, right? Not at all.
well, I mean, actually, yes, but they're going to scale with the system size.
Okay, so they're not
They're not LDPC if you want to define it this way.
Okay.
Right? I mean, I have to, yeah. I mean, in specific versions of the crypto system, there exist many like different variations of the crypto system that one can play with. I'm not aware of any like fixed weight situation that you can hook up with, but you can, yeah.
We should talk.
Yeah, but in general, we expect that you need to like go to like really high weight, like high connectivity. So that's not good. This is a coding theory. It's not a practice.
Other questions?
I'm not sure if it's the same question because I'm not sure what the weight is here, but in terms of connectivity between each mode, like
it's
the same question or
it is a similar question. Yes. So yeah. So it's in this situation. So the original version of GKP of the NTRU system implicitly puts like a handle on like how say non-LDPC is. But LDPC now not in our Euclidean sense, but LDPC in the coding theory sense, right? So that you only have like a finite number of entries in your matrix. So that these versions exist. There exist parameterizations that you can use, but in order to really go to the good distances, you need to let that thing grow. You need to let the non-locality grow, and that's certainly a very big drawback. I don't know if we can come up with a similar construction that is like closer to the actual LDPC kind of thing, which I doubt it. But.
Right. I think we can thank the speaker again. And the next